if it's early in. And please, the floor is yours.
Okay, let me share the screen. Okay, well, first of all, thank you for inviting me to give this presentation. So today I will talk to you about the dust proxy records from Iceberg Alley across the mid-Pleistocene transition and a little bit beyond that. Part of these major results are based on IODP Expedition 382, which happened in 2019, and we are still working on those samples and the results. And down here, there is a lot of colleagues mentioned that accompanied this research also over the years, over the last decade mainly. So what I will talk today about, I will start off by showing you that there are common millennial and orbital scale climate variabilities imprinted in the dust record around Antarctica. And then in the second part, I will go to a paper that raised the interest of the ice core community, which is about anti-phase dust deposition and ocean productivity in the Antarctic zone over the past 1.5 million years. And that is a paper that actually draws the conclusion that sea ice should be a major player, a major driver in the changes in the carbon cycle across the mid-Pleistocene transition. Then I will go a little bit more into details about comparing our new dust record from U1537 in the Antarctic zone. I will compare it to ODP site 1090 from the subantarctic zone and hopefully be able to convince you that this new record is probably the template you can expect if you drill ice through the mid-Pleistocene transition. And then at the end, I will do a short interhemispheric comparison of dust records to site 1208 from the North Pacific, which provides compelling evidence that we have synchronous changes in dust and global aridity since the mid-Pliocene. So let's start off with a paper that we published 10 years ago. This was actually not really about the dust, but we used dust as stratigraphic tool. As you can see here, this is Patagonia, which is the major dust source for Antarctic ice cores, and the southern hemisphere westerlies. They blow this ice, these dust to the ice cores in Antarctica, such as shown here in EDML, but also in the ones further away, like EDC, which I will also show today. And as you can see, these cores are immediately in the trajectory, and they are very close to the source, so we could already expect that we get a pretty pristine dust record in the ocean. And we used it there as stratigraphic tool. You see here what we did is we compared our dust proxy records to one of EDML, which is the non-sea salt calcium flux. We used also calcium, which we can be sure is also a detrital component because these sites are located underneath the carbonate compensation depth. So calcium is not biogenic. We also used iron for these comparisons, and the most trustworthy dust proxy record we can have, which is magnetic susceptibility from these two different sites. So what we did is we looked at common changes in the breaks of these slopes to define throughout the last deglaciation 5 stratigraphic type points between 19 and about 8,000 years ago. And that let us build the basic high-resolution chronology here. And if you're lucky, and we were at that case, you can also throw in an ash layer, which occurred just a little before 15,000 years ago. And that is expressed in the ice core, and we also found it in the marine core. In fact, we have now one topic that we try to create a volcanic template over the last 200,000 years where all the marine ashes could be tied to ice core ashes in order to improve this chronology. This comparison also shows a dilemma with the ocean cores. In the ice cores, you can actually measure dust as a detrital particle. In the ocean, it's not so trivial because particles can be delivered by the atmosphere, but also ocean currents can deliver it. If you're close to a continental margin, even distal turbidity currents can deliver it, and even icebergs can deliver it. So we always only can measure proxy records for dust. We can never really confidently measure it directly. And now we go back to orbital scales. This is the EDC dust record over the past 2 glacial cycles given at the top. And this is again from these earlier cores retrieved with Marion Dufresne in 27. This is the record over the last 2 glacial cycles, again, the dust. And if we use these gray little vertical lines as type points, we can tune the one record to the next one. And at the bottom, you see now from our recent IODP expedition, the same dust record, which is a little bit lower in resolution. But what it shows clearly is dust is always enhanced towards the late glacial phase. That's when the amplitude increases, and that's when we can provide a very good chronology. If you go, however, to the peak warm times, like here, marine isotopic stage 5 and 5E, the dust signal is relatively flat, so it doesn't really serve as a good stratigraphic correlator. So let me show some results of our IODP expedition 382. The main 3 sites we retrieved are here 1537, 1536, and 1538. The important thing is they all reach past the mid-Pleistocene warm period. And that is important to study all the warmer than present day climate variability, and also the development of the Northern Hemisphere glaciation, and also the development across the mid-Pleistocene transition. So we provide with this expedition, and specifically our star site 1537, which I will report here, the first documentation of the past Antarctic ocean atmosphere dynamics, covering all the important climate tipping points. And this is again from a paper of Andrea Dutton, meanwhile 8 years ago, that shows you why this is so important. Because if we go to these past warmings, we see that either sea level, CO2, or temperature were higher than they are today. And these are all the possible scenarios that we discuss for the future Antarctic ice sheet. And to obtain a record near Antarctica that is continuous and of high resolution, that is really important, and we were glad to be able to retrieve this. Now let's briefly talk about this paper we published 2 years ago. The story here is that we knew from the subantarctic zone that during glacial periods, productivity was enhanced, but also dust was enhanced and delivering iron to the sites in the subantarctic zone. And this is why people could infer there was higher productivity there and higher CO2 withdrawn from the atmosphere during these cold periods. We wanted to see how that is in the Antarctic zone. So if we go to our site on the left, you see dust trajectories, and this is for site U1537. You see this is in the Patagonian trajectory, relatively close. If you compare that to 1090, that's already pretty far away with a lower concentration, but still both would be good to trace dust coming from Patagonia. If you go to the right, that's the chlorophyll indicating that the dust is, that productivity is also high in 1537. That's the same is true for 1090. So for today's correlations, we see that this is the case. Both of these 1537 and 1090s are good places to study these phenomena. But let's go back in time. So here on the left, you see 2 proxy records. The one is color reflectance B star. That's a proxy for paleoproductivity, and magnetic susceptibility on the right. That's a proxy for dust. And I display this for the top 200 meters of that site, and that equates to about 1.5 million years. Now, what we do is magnetic susceptibility. We measure on the whole round part. This is the red curve. And later on, we use a point sensor with a higher spatial resolution to measure it again. You see that curve is a little bit more spiky. But we do not only do that in the ocean. It's typical that we go ahead at the very same site and drill a second almost identical hole. And the reason for that is that you see this black bar here, it gives you the core recovery. Well, that's pretty good. It's not really as good over here. But most importantly, in the drilling process, you retrieve a 9.5 meter long section. And at the top of that section, you may have some fall in, and at the bottom, you may have some disturbance. So it's a good idea to have a second hole. And we try to offset this one. And later on, what we do is we take the best bits and pieces from both of these holes and create an idealized hopefully rather perfect continuous splice record, okay? So, and all the graphs I'm going to show from here on out are based on this splice record, which hopefully has a better quality than a single hole record. Just a few words on the chronology. We have a basic ground truth chronology, which consists of magnetic reversals. These are the gray symbols you can see here. And we have 12 of them. They are absolute fixed points. It's known when Earth's magnetic field has reversed in the past, and we can use that as time markers, as a barcode in the sediment. And then accompanying, but not really taking as a direct age control, is biostratigraphy. So you see these left triangles, triangles in purple pointing to the left. This is the first time a specific species occurred. And then you see the ones in orange that point to the right. This is the last time a species occurred. And we had about 18 of those events over the last 4 million years. And what we did then, based on that and based on dust proxy records, we tuned the record using 183 tuning points over the past 4 million years. And those are the black dots in the center. So how can we justify the tuning? This is our U1537 record with magnetic susceptibility plotted relative to the Lisicki-Ramo stack. And note that the axis is flipped with magnetic susceptibility. What we see is that at each magnetic reversal, if that happened during a warm time, dust was low. If it happened during a cold time, dust was high. And if we now extend the record back to 3.3 million years, we have another 8 of these magnetic reversals showing us basically the same. If it was warm, dust is low. If it was high, dust is high. And if it's on a transition, then dust is on a transition. So we see that throughout the record, there is a stable phase relationship of the occurrence of dust relative to climate, in this case, an ice volume proxy. And we use that information to tune our record over the duration of EDC, that's the last 800,000 years, to EDC. And below that, we tuned it to the cold periods of the Lisicki-Ramo stack. Now let's go ahead and compare that. So this is the dust flux from EDC over the past 800,000 years. And this is the same dust record from our ODP site 1537. And as you can see, the correlation is really stunning. Every tiny little detail correlates. And as you also might see, some of the spikes are even a little bit more pronounced in site 1537, which is not surprising because it's much closer to the main dust source. And this very close correlation led to the expression that this is probably the ice core of the ocean. For you guys now, it would be interesting in the search of oldest ice to obtain something like a continuous record across the mid-Pleistocene transition. So how might it look like in terms of dust? Well, we have obtained this over here. And 2 things I would like to say here. First of all, what we see is that the amplitude of dust variability remains high throughout that period. But we can also see that the frequency changes here. It's more a response to 40,000 years obliquity cycles, and here it's more a response to eccentricity cycles. I will come back to that later. What's also interesting is if we look again at a comparison to the Lisicki-Ramo stack and again flip the record and plot it logarithmically, we see that there is indeed a very, very close relationship between the dust and the global ice volume / temperature proxy here. And as I told you before, dust always occurs during the cold times. But what we observed in the Antarctic zone, which is opposite to the subantarctic zone, productivity was not enhanced during that time. In fact, also very monotonously, productivity was enhanced during the warm times. So let's show this in a separate plot here. This is again the top 200 meters, 1.5 million years. And on top, we see our our productivity proxy B star. And on top, these white dots are actual measurements of opal content. And we used another proxy for productivity, which are ratios. In this case, the ratio of silicon versus aluminum, which is a biogenic versus a detrital component. And we see the very same trend. Over the past 25 glacial to interglacial cycles, interglacial productivity was always enhanced and the glacial productivity was more or less at a base level. But across the MPT, we also see interesting long-term trends. So before the MPT, before 1.2 million years, we had rather high variability. Then during the MPT, basically the time 1.2 to 0.7, 0.8 million years, we had low amplitudes. Then during the last 3 to 4 lukewarm interglacials, we have a stepwise ramp up in interglacial productivity increases. And since the mid-Bruns event, the last 4 glacial cycles, we had the highest productivity in interglacials. So we see that there is a sort of a stepwise increase which follows the low eccentricity 400 kiloyear component in productivity. So if we conclude that story, as I told you, in the subantarctic zone, we knew that dust was high during the glacial, and this was also the time of high productivity and could provide an explanation for the active atmospheric CO2 drawdown during the glacials. This is somewhat different in the Antarctic zone. We see high dust supply but low productivity. And the reason for that is, and I didn't show you the details, it's in that paper, that we infer severe sea ice coverage, both for winter and summer sea ice, which would reduce upwelling and lead to a more stratified ocean. And that would prevent CO2 to exhale in the atmosphere and keep it in the ocean. And that would be the contribution of the Antarctic zone to lowered glacial CO2. Okay, let's compare dust records. What I've done here is a little bit more of tweaking. We took the magnetic susceptibility record and normalized it and also brought some lower resolution into it to only see the stable orbital signals in the record. And then we did the same for the calcium record. And also we did the same for the iron record. That's a good thing because iron as a fertilizer in dust, we can directly compare it to ODP site 1090. So if we normalize all of 3, what we can do is then we stack these records and normalize them again. And that would be the record at the lower bottom. And that should be the most robust representation of dust transport in Iceberg Alley. And if we compare that to the EDC dust flux record, of course, obviously they correlate, but I want to emphasize again, the best correlation is probably given for magnetic susceptibility. Now, what we can also do is we can convert that magnetic susceptibility count record into an accumulation rate. But since the accumulation rate is high during glacials, that curve will even become more spiky. So the glacial to interglacial amplitude is gigantically high, at least 1 to 20, up to 1 to 50 or even more. And if we take that dust accumulation record and compare it again to the dust flux record of EDC, we really see that there is an astonishing correlation between the 2 sites. But I need to tell you that the same kind of very good correlation for the duration of EDC is also given for ODP site 1090. The difference is before that. If we go to 1090, we see that before the mid-Pleistocene transition, the average amplitude was lower, and only during the mid-MPT, here between something like 1.2 and 0.9 million years, the subantarctic zone was included into that system. And since then, they are really vertically identical. And there was a paper here last year in ETU Sphere evaluating marine dust records as templates for optical dating of oldest ice. You may read that if you're interested. So let's look again a little bit at that spectral evolution. I was showing you before that until 1.2 million years, we have a very strong obliquity forcing in the signal. And then we have sort of a covariation. And since 0.7 thousand years, this dominance of the entricity cycle. And how does it look like in the other records? Well, if we go to the right here, the Lisicki-Ramo stack, that has virtually the same strong 40K component, and then this transition and 100,000 years. But we don't really see that strong 40K component inside 1090, but we do see identical behavior after something like 700,000 or 800,000 years before present. So there are some differences that only are made for 1090. The Lisicki-Ramo and our dust records show some similar behavior there. So let's dive a little bit more into these differences. This is again the top 1.5 million years of ODP site 1090, and that is our record. You can already see that over here the amplitude is higher. But now, how does it look in even older timescales? So this is on the same timescale, 1090, for the time back to 3.4 million years. And you see already at that very high resolution, you have some data gaps and clipping over here. And if we plot on the same scale our dust record on top of it, you see it maintains this long-term variability. Or if you come from time right around until maybe 2.7 million years, the records were more or less identical, but then U1537 starts to depart, and that increase, it's very important because that's the begin of the intensification of the Northern Hemisphere glaciation. So since then, apparently, there is a development in U1537 that is not documented at site 1080. And if we compare now our dust proxy record over the past 4 million years to a proxy record from the North Pacific site 1208, we see that there is very interesting and compelling correlation between the two sites. First of all, we do see that right around 3.3 million years, there is this initial jump in the record, and that's the initiation of the Northern Hemisphere glaciation. And as I showed you before, also commonly expressed, starting with at 2.7 million years, there is this common increase, and it's always during the glacial that both records are enhanced. So based on these commonalities on an interhemispheric scale, I would say it's more likely that 1537 is the sort of template you could experience if you are to drill ice that goes through and maybe beyond the mid-Pleistocene transition. Okay, so let me wrap up. Marine sediment cores in Iceberg Alley, they show a robust dust climate coupling on millennial, orbital, and also on long-term Pleistocene timescales. The dust records in Iceberg Alley are located in the direct trajectory of the major dust source Patagonia. Then we retrieved the highest resolution decadal scale and stratigraphically longest 4 million year continuous record of ice-ocean atmosphere variability near Antarctica. And the dust record for marine sites in the Antarctic zone, which is our site 1537, and the subantarctic zone, they co-vary similarly over the last 800,000 years, the duration of the EDC ice core. However, if we look at the time before that, the Antarctic zone and the subantarctic zone dust records start to synchronize between 1.2 and 0.9 million years, accompanied by a transition from the obliquity to the eccentricity forcing. And prior to 1.5 million years, the subantarctic zone was apparently not coupled to the global dust system. And as I just showed you in the last example, since the initiation around 3.3 and the intensification of the Northern Hemisphere glaciation around 2.7 million years, we infer synchronized interhemispheric increase in global dust deposition and aridity documented in the Antarctic zone and in the North Pacific. So that was it. Thank you for your attention.
I can talk.
Yes, so hi everyone. It's my pleasure to introduce our next speaker, Eric Wolff. So Eric trained as a chemist at the University of Cambridge and undergraduated in 1978. And then he worked at BAS at the British Antarctic Survey in Cambridge for several decades. He got his PhD in 1990. And at BAS, where he was for many years, he became one of the science leaders. And in 2013, he became a Royal Society research professor at the Department of Earth Sciences at Cambridge University. Eric is widely recognized for all the work that he has done on Greenland and Antarctic ice cores, and his work covers a large range of topics such as long-term paleoclimate and atmospheric chemistry, especially looking at quaternary interglacials or millennial scale and rapid climate change, polar tropospheric chemistry, just to name a few of the topics that Eric has worked on. Eric was also the chair of the science committee for the European project EPICA that produced this iconic record from EDC. And for many years, he was also a co-chair of the international initiative IPIX that is coordinating ice core research. And he received also prestigious medals, including the Louis Agassiz Medal by the EGU in 2009, and more recently the Richardson Medal by the International Glaciological Society in 2020. And so Eric is actually freshly retired since last Monday. But luckily for us, he will remain active in science a little while longer, and he's doing us the favor to give this talk today, entitled Dust in Ice Cores, Stratigraphic Markers and Proxy for Transport and Terrestrial Source. Eric?
Thank you very much, Emily. Is that showing up okay? I think it is. Yes, I don't like hearing that I've retired and that I've been working for decades, but I'm afraid it's true. So thank you for the introduction, and thank you to Mike for his really interesting talk. He sent me his talk in advance, and so I knew he was going to give me a bit of a dilemma, because both of us could have talked about the correlation between ice cores and marine sediments, but he's really covered it. So there's really very little for me to say about that. I will come back to it right at the end of the talk. But I decided that perhaps the best thing to do was to talk at a more general level about what dust in ice cores is about and what we might hope to get out of it. I think we're still struggling a little bit to interpret what dust in ice cores means a little bit. I put about transport and terrestrial sources, and I think the balance of which of those we think is more important has oscillated over the last actually 30 years with different papers coming out, and I think we're still oscillating a bit, and we really need some help from modelers for that, and therefore this is a perfect forum to raise this issue and ask for that help. I'm also very aware that there are many other people who work closely on dust on this call, and so I hope they won't object too strongly to the things I'm going to say. So here's the contents. I'm going to talk about what we mean by dust in ice cores, what the data look like, where the dust actually comes from. I'm going to talk about Greenland and Antarctica for this talk, so not just concentrate on Antarctica. And then I'll get into what causes the change, and then finally onto the dust templates. So why do we want to know about mineral dust, going right back to the first principles? Well, it's the most abundant atmospheric aerosol after sea salt. It's very important for the radiative energy budget of the atmosphere. And it's very important, as Mike was talking about, for the primary biological productivity in the ocean. So iron fertilization and similar processes. So ideally, what we would do is to use ice core and marine concentrations to give us some ground truth. And along with modeling, we would then derive climate-dependent emission rates, concentrations in the atmosphere worldwide, and deposition rates to land and the ocean, and we'd have everything we needed to know. And indeed, people have attempted to do that. I think Fabrice has published a paper where he used the data to try and interpolate worldwide what the concentrations and deposition rates would be. Okay, firstly, we should talk about what we mean by dust. So normally when ice core people talk about dust measurements, they normally mean insoluble dust particle numbers and sizes, which are measured either with a Coulter counter or a laser scattering device, normally an abacus. So when you hear people talk about an abacus, they don't mean they're counting the dust on a little counter. They mean the laser scattering device. But we often also are a bit lazy and refer to other soluble indicators of terrestrial material like aluminium, calcium, or iron. And we often use those interchangeably, at least I do, and I guess several of my colleagues do. So let's look at, I should say, I mean, that's an interesting point. We do at least know that what we're looking at is all atmospheric dust. We can correct for the dust that isn't coming from terrestrial material pretty easily. I might refer to the fact that in the ocean it's harder because there are other sources of dust, and I think maybe we do need to come back to that a little bit when we discuss the dynamic range as to how sure we are that, you know, which of the proxies is really telling us only about terrestrial dust. That was probably partly the meaning behind Hubertus's question. Okay, so what do the data look like? So this is Greenland over one glacial cycle, going back 120,000 years. Oh, I've broken my cardinal rule of putting time going from left to right here, sorry. So time's going from right to left. So what you can see here, you've got the North Drip delta 18O on the bottom and the dust in particles per milliliter, which is what was measured there. You can see that it's very high in the cold periods, particularly the cold stadials. So actually the highest numbers are not even in the last glacial maximum, they're actually in some of the cold stadials. And you can see there's a dynamic range of about a factor 100 in dust between the Holocene and the maximum in the cold stadials. And you can't see it on this plot, but there are really sharp transitions when you go from high dust to low dust. So that's as you're going from cold to warm in a Dansgaard-Oeschger warming. The dust is changing by a factor of 10 in something that's of the order 2 or 3 years. It's a phenomenally quick change, which already tells you something about what the mechanisms must be. So if we go to Antarctica, this is Dome C in blue and Dome Fuji in red. Again, we've got the isotopic record on the bottom to orient you, and the marine isotopic stages labeled there. And you can see what the dust is doing. Actually, I can't see because I've managed to make my screen so that I can't see the right-hand side of it. Just a second. Okay. So the dust again has a very huge dynamic range. Don't think I'll turn it. Yeah, I've now put it on a log scale to make it a little bit easier to see firstly the agreement between Dome Fuji and Dome C, which is absolutely phenomenal considering that they're on opposite sides of the continent. You've got very high concentration in glacials. Again, in the concentration, there's a dynamic range of about a factor 100 there. This identical pattern across Antarctica has been used to try and date ice cores in the past. For example, it was used in dating Taylor Glacier, and indeed it was actually used to show that the initial age model for Taylor Dome, which suggested some rather surprising ideas about the timing of change in Taylor Dome, that the dust was used to show that that original age model was wrong and to suggest a more correct age model. So it's been important already, this huge similarity of dust across Antarctica. So now let's go a little bit conceptual and think about what controls the dust concentrations. This is actually a very old figure from a paper that I was involved with Katrin Führer 25 years ago now, but it's still a nice simple conceptualization of what's going on. So the first thing that could be changing is the source strength, and that doesn't just mean the size of the source or the nature of the source, which would obviously be changed by things like vegetation being present or not, but also by the wind speed. The pickup of dust from, I'll come back to it, but the pickup of dust from sources is very strongly dependent on wind speed above a certain threshold to a power of 3 or 4. So a small change in wind speed can make a big difference. Then you've got to uplift the dust to the transport levels, and then as it's transported, it says transported over pole because that was talking about Greenland with transport from Asia, but it's transported to higher latitudes. You've got deposition all the way en route, and that could cause losses as material is taken out of the air mass during its journey by wet deposition in particular. And then finally, you've got the deposition to the ice, and obviously the dust is diluted in the core depending on the accumulation rate and the ratio of dry to wet deposition. So there are these 3 kind of major factors that could be affecting the concentration. There's what's going on at the source, what's going on during the transport, and what's going on when it's deposited. So we need to step backwards before we talk about what could be happening at the source and the transport to think where the dust is actually coming from. This is a map that was in a paper about a decade ago, but I don't think it's substantially wrong of where we think the main sources might be. It comes from arid and semi-arid areas, obviously. There's a long history now of geochemical fingerprinting, and I think Barbara Del Monte, who did a lot of this work in Antarctica, is on the call. It's mainly used strontium and neodymium isotopes, sometimes lead isotopes, sometimes element ratios in mineralogy. And I'll talk a little bit about what that shows in a second. There's just one thing that I actually want to point out on this map here. Have I got a pointer? Laser pointer, there we go. There's one thing I want to point out here, which is a trivial point that I think most people, if you ask them where are the main deserts in the southern hemisphere, they would tell you Australia. The critical point why South America is so important which you'll see that we think it is because it's so much further south, basically, as a source. And this is the only map I've got where that's really obvious. So I just want to point that out. You can actually see, as just a side effect, that in this particular estimate of where the deserts and dry areas were, they made a big deal out of the new bits of continental shelf in South America during the last glacial maximum. We've had conflicting ideas about how important that might be, and again, we might come back to that later. So for Greenland, sorry, I've used a very old paper from Anders Svensson and colleagues. Most papers have concluded that the main source is Central and East Asia, using neodymium and strontium isotopes. That implies a long high-altitude journey in the westerlies to Greenland, which is why that previous conceptual plot had the westerlies written on it. But there's a recent paper by Gabor Ujvari, who I think is also on the call, using the same isotopes, but also hafnium isotopes, which has opened up the debate again, I think, suggesting that another option that would actually fit the isotopic data for Greenland would be a mixture of dust originating from Europe and North Africa. So it doesn't rule out the Asian sources being important, but it adds the possibility that there's a significant source from Europe and North Africa, and maybe Gabor would like to comment on that later. For Antarctica, so it's again neodymium and strontium isotope plots. Most papers have concluded that South America is the main source, certainly in glacial periods. Patagonia and the Puna Altiplano Plateau further north are mentioned. There's a range of South American sources that could be involved, and there have been more recent papers suggesting that. That's probably something I should have said, that for both Greenland and Antarctica, I think the main stopper on actually fingerprinting these sources is not to do with the measurements in the ice, it's to do with the measurements of potential source areas. There are so many potential sources in the areas that have slightly different isotopic signatures, and many of which have not been sampled. For interglacials, it's possible there could be some Australian input. I don't think it's actually essential, is my reading of the paper, to have Australian input. I think you could still do it with only South American input. But anyway, when we're talking about the glacial interglacial dynamic, it's the huge increase in the glacial, which we're pretty convinced is South American, that's important. So going back to what factors determine the dust concentration, which is why do concentrations increase by roughly a factor of 100 in glacial periods? So a first factor is clearly the reduced snow accumulation rate. So that's that bit right at the end of the process where the snow is deposited onto the ice. We measure the concentration, but if dry deposition is dominant, then we should really be worrying about the flux, because that's what's determined by the atmospheric concentration. So we actually expect that if the snow accumulation, that in a place where dry deposition is dominant, if the snow accumulation falls by a factor of 2 in the glacial, then the concentration will double in the ice core. And actually, you can get up to a factor 3 change in snow accumulation in Greenland and Antarctica in the glacial, decrease in the glacial. So you actually expect the concentration to increase for that reason. And so if we just take that out of the equation, we're actually asking the question, why do the fluxes increase by a factor of, shall we say, 30 to 50? And the critical point is that the models, to my mind, unless there's a modeler on who wants to disagree, struggle to get close to that. Most models that have looked at this, going right back to papers by Natalie Mahueld 20 years ago, in order to get anywhere close to the Antarctic value, they have to evoke a kind of exotic source that they've made up. It's not really a source they're sure is there, but they kind of evoke it for the glacial. In Greenland, I think they really struggle to get close to the right values. They have to say that things are going on in Asia that we don't really know are going on in Asia. They don't really get very much from the transport, which is interesting, and I'll come back to that. So going back again to what might cause an increase in the flux in the glacial, as I said, it could be the change in the source, which could be the latitude, the source area, for instance, the continental shelf, aridity and vegetation and wind speed. It could be a change in lifetime relative to transport time, which could be change in transport speed or wet deposition. And probably the truth is a bit of both, and most papers written in the last 3 decades have kind of tried to say it's a bit of both. But the issue is to tease them apart, and various authors have attempted this over the years. And I'm going to give you a couple of examples of how this has been done, some of the more recent ones, and then come back to what we think about it. So for green, the most recent version was the approach by Simon Schut back in 2018, where he just assumed that the change, so he just looked at the change in, sorry, go back a second. He used this idea of the change in the lifetime of the dust, so that's the tau in that equation, compared to the transport time, to try and back out what the concentration was at the source. So C air is the concentration above the ice core site, which we are equating essentially with the concentration, with the flux in the ice core, the flux of dust to the ice core. And then by using this equation, you can get back to the concentration at the source and say how the source concentration changed. So what controls that tau value is mainly the precipitation rate en route. So as you're going along in a single air mass, every time it rains, you're taking dust out of the air mass. In that paper, he assumed that the source location remained the same, and in the base case, he did some sensitivity studies, but in the base case, I think the transport time stayed the same as well. And what he came up with is shown in this plot here. It's on the top, the calcium. It's not actually dust, it's calcium. So the solid brown line, if you can see it, is the ice core data. The dashed brown line is the atmosphere above the ice. So that's essentially based on the flux. So that's taking into account the flux. You can see it's on a log scale, so there's a factor 2 or 3 taken out there. And then the brown line is what you get at the source, where the wet deposition has made a difference, but still the source has had to change by roughly 1 order of magnitude between Holocene and high glacial periods. So he concluded that there was a significant influence of the losses during transport, but that most of the dust change was due to changes in aridity and wind speed at the source, assumed to be in Asia. So then a different approach has been used most recently in Antarctica by Brad Markle, and he did something slightly different. It's in a certain way, it's conceptually the same, but it's a slightly different way of calculating things. He noted the close relationship between aerosol and water isotopes, and he made the concept that if you had an air mass where water's moving from the warm source latitudinally to a cold sink, water vapor is progressively removed, and that's exponential with temperature. It's a Clausius-Clapeyron process, which drives the isotope profile. But the water vapor being removed is actually rain. So that's a progressive rain out along that same trajectory, which also removes aerosol. And you can use the removal rates that are known from the modern of aerosol in rainfall to estimate how much is removed by a particular amount of rain. So by coupling these, the isotopes or temperature, the precipitation, and the aerosol removed by wet deposition, you can make a model that estimates the change in aerosol due to the lifetime of the dust. And that's what he did. It's in the blue line for calcium. The dots are the data, and the blue line is what the model does, what his model does. And you can see that with his preferred parameter choices in Antarctica, he argues that most of the dust change might be due to wet deposition on the journey, and that there's very little change at the source. If he's correct, there's no need to find a change in the source in South America at all. But I would argue, and this may be the starting point for discussion in a couple of minutes, that the jury is still out. Because especially for dust, it's normally assumed that over deserts, that dust is lofted high into the atmosphere in order to get transported a long way. And if it's lofted high into the atmosphere, then it's above the cloud level for most of its transport, which challenges the concept of the model. In other words, the aerosol that we see is not traveling with the water vapor that makes up the isotope signal. And that makes sense because, after all, the air mass that contains the aerosol is generated over a dry desert. So it's highly unlikely that it's got in it much of the water vapor that eventually causes the isotope signal. So although they do appear coupled according to the data, I struggle a little bit to see how they're coupled in reality. It's different when you're looking at sea salt or sulfate, where they're generated in the marine atmosphere, and therefore you'd expect them to be coupled to the water vapor. A second problem is that GCM studying dust, as I mentioned earlier, tend to find a rather small change in lifetime. And that doesn't just mean when they go back to the LGM where you don't quite know what's happening, but also in sensitivity studies where all they did, in this paper by Lee et al., for example, in 2010, all they did was to alter the wet deposition rate, and they found a rather small change in the amount of deposition in Antarctica. And I don't actually know why that is. They don't actually say why it is. But I think what we urgently need is a reconciliation. The question is, why do the large changes in lifetime that the conceptual models suggest should occur not occur in GCMs, and which of them is right? Because until we can get that right, it's inhibiting our ability to use dust in ice to understand climate. One additional comment on this, we, and that does include me, I've said it and written it, often say that since the South Atlantic cores show a factor 5 to 10, I think Mike may even have shown something slightly higher, increase in deposition, while ice cores show a factor 50. The ocean ratio is the maximum change possible at the source, and therefore the rest must be due to lifetime and snow deposition. I'm actually not sure anymore that that's right, because actually these same processes should cause the amount deposited to the ocean in the last glacial maximum to be less, because there's less wet deposition into the ocean. And so with lower glacial precipitation, the deposition to the ocean should fall. So actually the ocean dynamic should be a minimum value for the change at the source, not a maximum value for the change at the source. So summary for that part, there are huge changes in dust deposition across glacial cycles and across DO events, but we still have a lot of uncertainty how to partition this between changes in source and changes in lifetime. And I think we really need modelers to engage with the conceptual ideas and explain how their parameterizations deal with those concepts. How do they deal with the uplift? Why doesn't wet deposition seem to make much of a difference to the amount reaching Antarctica? We can still use the changes to tie ice cores to each other and to Southern Ocean marine records, and I've just got 2 slides here, I think. So we do get this very close relationship that Mike talked about. In this case, I've put on 1123. And then there is this paper by Ung et al., which has now been published in Climate of the Past, suggesting that 1090 might be a better template. I agree that it's a much nicer core. It's got much better resolution. I still feel a little bit queasy about saying, oh, it's near to the Patagonian source, so it must be better. I think you could argue it the other way, that if the source is actually covering quite a wide latitude range, as the fingerprinting data suggest, then something a bit further away might be better integrating that. So I think just let's wait until we get the core and see which of them it looks like, and hope that it looks like one of them and maybe not like the other one. So that's it. Finally, the dust is only one method we'll use to date our old ice. We'll hopefully have a lot of continuous things to tie ourselves to using orbital targets. We'll hopefully have some absolute dates as well. And which ones are most important will depend on how continuous the ice core actually is. Okay, thank you. I'll stop sharing.